Let's proceed with our lectures, and this lecture will be connected with solution of schematics with transient processes in branch circuits with a capacitance. It may be proved that if we have arbitrary complex schematic with only one capacitance, and in such a case, we can write down equation which depict electrical processes as follows. It will be R equivalent multiplied by C duc by dt. You see, its voltage drop across equivalent resistance plus UC voltage drop across capacitance equal to F from T. What is F from T? It's function which depends on type of the applied EMF after commutation. If no EMF or current source is applied after commutation to the considered schematic, this F from T will be equal to 0. If it is DC EMF is connected, this will be of DC type, and if it is AC, it will be of AC type. And these are equivalent. It is active resistance of the circuit after switching relatively capacitance terminals when this circuit is represented in the so-called passive mode. I will explain you on the examples later on. And tau C, time constant, will be equal to product of C and R equivalent. And solution of this equation can be written as UC equal to UC forced plus UC natural. And UC forced is a forced component of the solution, and UC natural is partial solution of this equation with zero right hand side. UC force equal to U is phi T is constant, capital letter, means UC force equal to UC maximum sinus omega T plus U phi UC if phi from T is this considered schematic is connected to the sinusoidal function. It is 0 if the considered schematic will be disconnected from the source after commutation. Natural component does not depend on the type of F from T, and it all times is written as product of integration constant and exponential function minus T over tau C. And this integration constant can be determined and should be determined from the second switching law, from the condition UC from minus 0 equal to UC from 0 plus. Current through inductance is determined as follows. It's C duc by dt. And rest of values of natural component in the considered circuit should be determined with the help of this UC natural and this IC natural. This current and voltage drop should be considered as sources of natural components of currents in the other branches. And we should use this natural component, UC natural and IC natural, for determination of other natural components. What it means here are equivalent. We should let's consider an example. For instance, such an example we have here. We have here not so plain schematic, and I would like to remind you that electrical circuits which contain only one reactive element, either inductance or capacitance, they are described with the linear differential equation of the first order, and therefore such circuits are called circuits of the first order. You see, this equation, it's first order differential equation, and the same, not the same, but analogous equation of the first order has been used for determination of transient processes in RL circuits. So let's consider this example. We have a branch, RC branch, and before commutation, it was this key was in the first position, and after commutation, it will be in the second position. I would like to remind you that here EMF it's designated as capital letter, so it's constant DC EMF, and therefore in steady state regimes there will be no current through the branch which connect capacitance. So IC here will be 0. IC steady state. At t less than 0, therefore, this current was absent, and current has been flowing through such a loop. Okay, so we can write down that here this I from t current equal to E over R plus 2R, E over 4R. Okay. And voltage drop across this capacitance, it was not any current here, but it was voltage drop. And this voltage drop, you see, this branch and this branch were connected before commutation in parallel. But in this branch, it will be no current. So, it will be no voltage drop across this 3R resistance. Therefore, Therefore, all this voltage drop across these equal to each other across these two branches will be applied to this capacitance. So, UC will be equal to voltage drop across these 2 points. But we direct this voltage drop from B to A. But voltage drop across this resistance is directed from A to B. Therefore, UC will be equal to UBA will be equal to minus UAB and equal to module of voltage drop across with minus sign across this resistance. It will be, you see, current here equal to E over 4R. Therefore, we should multiply this current by R, and it will be voltage drop here. It will be minus E over 4. So, therefore, UC from minus 0 equal to minus E over 4. It's voltage drop, initial voltage drop, UC from minus 0. For t greater than 0, we can write down that UC equal to UC forced plus UC natural. And UC forced will be constant because E constant, and IC forced by the same reason equal to 0 in steady state regime. So we can write down that I forced we can write down that I forced here in this schematic will be the same, equal to, for t greater than 0, equal to E over 4R, and IC forced in this schematic after commutation, when switch is not from is relocated from the first position to the second position, we will have such a connection. So UC forced after commutation will be equal to voltage drop between this UBC, and UBC will be the same direction as UC. So UC forced will be equal to this E over 4R current multiplied by 2R, so it will be equal to E over 2. Understandable? E over 2. So in this case, capacitor will be recharged. It was direction of voltage drop was to the right, and after commutation it will be to the left, and its value will change. So current here in steady state regime in this schematic will be the same, but this capacitor will be recharged. Let's determine now R equivalent. R equivalent, as I have told you, should be determined in the regime after commutation when this key in the second position relatively clamps to which this capacitance is connected, and the rest of schematic is considered in the so-called passive mode when we replace all EMFs and current sources by their inner resistances. And you should remember that inner resistance of EMF equal to 0, inner resistance of current source equal to infinity. So current source, for current source we should break a branch in which current source is connected, and for EMF source we should just short circuit it and remove this current source, like here, you see. And relatively these clamps in which capacitance is connected, we should determine these are equivalent in the regime after commutation when clamp is here, see. Okay, so let's consider these are equivalent. For such a schematic, this R and this R will be connected in series and in parallel to these two R. You see, this is one branch and in parallel to these two R. So 2R and 2R connected in parallel, the equivalent resistance will be 2R multiplied by 2R over 2R plus 2R. It will be equal to R. And this R is connected in series with this 3R. So R equivalent will be equal to 4R. Okay, it is written here. This 3R plus 2R over 4R. 2R plus 2R, 4R. So tau C will be equal to 4RC for such a schematic. So we can write down that UC, you mean for T greater than 0, will be equal to E over 2, its first component, plus A integration constant multiplied by integral minus T over 4RC, where 4RC is tau C. Then we should just apply second Kirchhoff law to determine this integration constant. You see from plus 0 will be equal to E over 2, yes, plus this item for t equal to 0, it will be just A, okay? And you see from minus 0, as we have determined, it was equal to minus E over 4, minus E over 4. So from this condition, we have this will be equal to this, okay? From here, A equal to minus 3/4 of E. We write down here its first component, it's A integration constant multiplied by exponential function minus T over 4RC. And from here, we can easily determine also IC, it will be C duc by dt, and derivative from first item from constant equal to 0. So we will have only natural component, and it is equal to derivative from this item by time multiplied by C. So if it is necessary to determine natural components in other branches, we should use this either UC natural or IC natural as a source, and we can apply here we can use here method studied in previous semester, when we can present current in each branch as sum of partial current from each source. For this, we will, and at this we will replace other current sources by their inner resistances. So it will be just from here, we will short circuited part, it will be R to R, 3R, and instead of this C, we will have EMF source, and it is directed this way because we have here minus sign, okay? So And for such a schematic, we can solve such a schematic and determine I natural. Here we can write down that we can write down that this I natural, yes, it will be equal to it is here, it is presented as EMF, but it may be presented as current source, okay? And if it is current source, we do know that current here will be equal to this IC natural, and will not depend on level of resistance connected in series with this current source, and therefore we have current which flow to two parallel connected branches, and therefore I natural current in one of these branches will be equal to this current UC natural multiplied by resistance of the opposite branch, it to R, and divided by sum of resistances of these two branches, 2R plus 2R equal to 4R. And then we substitute here IC natural, and we've got this IC natural. Okay, then we can write down that I forced I equal to I forced plus I natural. I forced, we don't know, it is equal to E over 4R, so it UC forced E over 4R plus this natural component. Okay, and we may calculate this value at, for the moment t equal to 0, and this is graph of IT. It was equal to this current I was equal to E over 4R before commutation, and it will retain the same value for steady state processes after commutation, but between these two states we have tension processes. At first moment I from 0 plus equal to 11 E over 32R, it is here, and then it will so it was steep change in current. It is possible because it is current not through inductance, and then it is tension process between these two states. And in the next lectures I will explain you how to deal with connection of RLC circuit to different kind of voltages, and we will get equation, the so-called equation of the second order. Now it is over. Bye bye. Don't miss lectures. Make your home assignments, please.